Okay, welcome to the lesson on properties of limits. So just to kind of motivate this, remember last time we had an example, I don't know if this was the exact example, but it was something like limit as x goes to 1 of x squared plus 1. And we knew that the graph looked like, okay, x squared plus 1, parabola shifted up 1, looks something like that. We want to do the limit at 1, and you probably know that the function f at 1, notice f at 1 is equal to 2, right? At 1, this function is equal to 2. And you can see from the graph that the limit at 1, we can see from graph that the limit as x goes at 1 of f at x is equal to 2. So the function at 1 is equal to the limit at 1. So, you know, do we have to graph it to see that, or do we have to do that table to see that? And, you know, the answer is hopefully not. And that's what the properties of limits, one of the things properties of limits is going to allow us to do. Evaluate limits without actually, you know, graphing to see what it's approaching or doing a table. Okay, so we're going to write down those properties and see how that will help us. Okay, so these two properties right here, these are our first two properties, and I'm not going to prove them, but I will, well, we'll do like a sort of intuitive explanation. So limit as x goes to a of c. C is a constant, right? You can think of it as a number. So like, what would the graph of that look like? You know, you can think of it like 2. So graph of a constant, right, if c was here, it would just be this line right here. So this is f at x equals c. X. That's y. Well, it doesn't matter where a is. The function is always approaching this same number, this c. So, you know, from there you can clearly see that it's c. Or if you did a table, right? If I took x equals to a, I don't care what a is. It could be anything, right? F at x. Whatever x is, f at x is c. C, right? 0.1, 0, I don't care what limit you're approaching, it's equal to c. So clearly that limit has to be c. So there's, you know, kind of, that one seems obvious. And then limit as x goes at a of x. Well, oops. What would that graph look like? That would just be the graph of y equals x, or f at x equals x. So if a is here, then clearly this has to be a also, because whatever the x is, the y is also equal to that, or think about that in a chart form. Whatever we put as x, right? A, then f at x is a. You know, if this is a number a little bit less than a, then this is a number a little bit less than a. So it clearly has to be going to a. So those are two basic properties, right? If we ever have that question, we can just sub them in. And then we use those to kind of develop some other limits. Or some, boom, what happened? So I wrote down the next set of limit rules, and you know, I'm not going to explain them at all, but we'll just kind of go over them. This one says that the limit as x goes to a of the sum or difference of two functions is equal to the limit of the first one plus or minus the limit of the second one. The third one says you can multiply by a constant, so the limit of c times f at x is equal to, and then you can kind of take that c out. The limit of a product is equal to the product of the limits. The limit of a quotient is equal to the quotient of the limits, provided that bottom limit doesn't equal 0, which makes sense because you can't divide by 0. And then there's a power one, so the limit of a power is equal to the power of the limit. So how are these going to help us? Oops. Okay, well, let's do an example. let's say I want to evaluate the limit as x goes to 1 of, let's take a big polynomial, 5x squared minus 2x plus 1. And now you might say, okay, I want to just sub the 1 in, and then that will give me the limit. And you're sort of right, but we don't actually have a rule which says that, right? We only have these rules here. So we could try graphing it, or do a table. But another thing we can do is break this up. So notice this is really the limit of this term minus this term plus this term. Well, we have a rule for breaking up sums and differences, right? This rule here says if I have the limit of something plus or minus something, then I can write the limit of just those individual things. So that's what I'm going to do. I'm going to write the limit as x goes to 1 of this first thing minus the limit as x goes to 1 of this second thing plus the limit as x goes to 1 of this third thing. So really I'm just using this rule right here. So I use property 3. Okay, so can I evaluate this one? Well, no, not quite, but notice it's a constant times something, and I have a rule for that, right? That was this rule right here. C times f of x, I can bring the c out. So in this case, the c was the 5. Minus, and then I can do the same thing. I can bring out that 2. Now I'll just have an x. Now this one actually I can evaluate, right? Limit as x goes to 1 of a constant. That was my first rule, right? Limit as x goes to something of a constant is just the constant. So I could have just wrote plus 1. And now what can I do with this one? Well, I don't have a rule for evaluating powers, but I do have this rule right here. I can make the power, f at x to the power of something, so I can take this power and put it outside the limit. So 5 of limit as x goes to 1 of x all squared minus, now this limit right here, that was my second property. If it's the limit of x, that's this property right here, right? It's just an x. As x goes to a, x will go to a. Kind of redundant. So this is just going to whatever x is going to. So 2 times 1 plus 1. And now that same rule, right? This went to 1. So 1 squared minus 2 times 1 plus 1 is equal to 6. Right? Oh no, it's not equal to 6, it's equal to 4. Yeah, it's equal to 4. So therefore the limit as x goes to 1 of 5x squared minus 2x plus 1 is equal to 4. And of course notice that really you could have just subbed the 1 into this. That if we call this f, call that f of x, notice that f at 1 is equal to 4. So really we could have just subbed in 1. And that's going to work for any polynomial. Hopefully you can see you could apply that to any polynomials. And we give that sort of property functions where that happens. We give that a special. So if the limit as x goes to a of f at x can be evaluated by substituting in a into f at x, So limit as x goes to a of f at x was equal to f at a, so that was like that last example, then we call this direct substitution. Okay, so when will this work? Works for all polynomials so that's what we saw in the last example, right? It works for all polynomials. So now when you're given the limit for a polynomial, you don't have to go and break it up all with those properties. You can just use direct substitution. Also, if a is in domain, then it'll work for a lot of functions if a is in the domain. It'll work for rationals. It'll work for square root functions. It'll work for basically composites of those. And you might be objecting saying, oh, rationals, didn't we do an example before where the limit didn't exist for a rational, or where there was a hole with a rational? But notice that I said this is the key point, is in the domain. So it has to be in the domain. So that means it can't be where there's an asymptote or a hole. But other than that, you're good. You can just use direct substitution.